Okay, in this video we're going to do sections, I forgot already, 7.4 and 7.5, as we've seen already. 7.4 is basically all the algebra stuff, and 7.5 is just applications of it. Now, 7.4 is a lot of me talking at you. I mean, you can respond if you want, but I won't be there to hear it. So talk really, really loud, and maybe on a wind I can hear it. Anywho, 7.4's got a lot of theory in it. The first half anyways, and then the second half has examples. So it may be the case that of all the sections we've done, this might be the most theoretical. If you need to watch the video again, you watch the video again. If you need to ask questions, you ask questions. Okay, 7.4, the Simplex Method, Maximization. So the purpose of this is because in 7.1 through 3, we only had two variables, x and y. But then the question was what if you have more than just chairs and nightstands? What if you had chairs, nightstands, tables, and desks? What do you do then? Well, you can't use two variables anymore. You can't draw this in two dimensions and use the corner point method, and that's because we're in 4 dimensions then, or 5 or 6, depending on how many variables you have. So how do you solve for that? You use this magical thing called the Simplex Method. The Simplex Method will be a combination of Chapter 6, mainly matrices and Gauss-Jordan, and corner point method, mainly linear programming problems. So all that together is 7.4, 5, and 6. What a great way to end the semester. Okay, we start off with a definition, namely the definition of a standard max problem. So in a standard max problem, 3 things must be true. The objective function is to be maximized. All the variables are non-negative, and all other constraints are written as linear expressions less than or equal to a non-negative constant. So, for example, we would have something like maximize z is equal to, I'm just making this up, 3x of 1 plus 4x of 2 plus 7x of 3. Oops, subject to x of 1 plus 2x of 2 plus 4x of 3 is less than or equal to 20. 2x of 1 plus, I don't know, we'll do 7x of 3 less than or equal to 15. And your x's are greater than or equal to 0. Alright, so notice some big changes. 1, we can't use x and y anymore because we don't know how many we have. So we use subscripted x's. 2, well actually that's really the only huge change, is you can't use x and y. So we use z for the objective function and we use x for the variable in a standard max problem. So keep that in mind. Z's, x's. We'll have different letters in 7.6 when we do a standard min. So the objective function is to be maximized. That's here, number 1. All variables are non-negative. That's down here, number 2. And all other constraints are written as a linear expression, linear expressions, less than or equal to a non-negative constant. So this is a standard max. You've seen standard maxes, we just didn't call them that. Well, I actually may have used that phrase earlier on. But in a standard max problem, they generally, if we had 2 variables, they generally would look like this. You'd have your function, you'll have your boundary lines, and you'd be shading towards the origin. So that's a huge thing, is I want you to think about, and we'll talk about later, every standard max problem, according to this definition, has a corner point in common. Just think about it for now. All right. So now what has to happen is we need to learn how to turn this linear programming problem into a matrix. And that matrix is called a tableau. But before we get there, we need to talk about what are called slack variables. Slack variables are the difference of the right-hand side and the left-hand side of a functional constraint. The difference of the right-hand side and the left-hand side of a functional constraint. I apologize. I'm going to go back here because I want to copy that stuff. I'll put it right there. That's fine. Hope I can erase it. No! No! I can't erase? That's silly. Alright, well, I guess I'll get rid of it then. I'll just make up another one. Okay. The right-hand side minus left-hand side. So, difference means subtraction. Look for the word and. So this literally means you're taking the right-hand side and subtracting the left-hand side. It has to be in that order. So let me just make up another one. Let's suppose we have 2x1 plus 3x sub 2 plus x sub 3. Well, we'll go crazy. Plus x sub 4 less than or equal to 7. And x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 is less than or equal to 10. Great. So you are only looking at the functional constraints to define your slack variables. So for every functional constraint you will have a slack variable. We have 2 functional constraints, which means we need 2 slack variables. We denote slack variables by s sub and whatever the number is. S sub 1 would be the first slack variable. S sub 2 would be the second slack variable. So for us, the right-hand side of the first functional constraint is 7, minus the left-hand side is 2x sub 1 plus 3x sub 2 plus x sub 3 plus x sub 4. Notice the parentheses, they're necessary. And then s sub 2 would be related to the second functional constraint. Its right-hand side is 10, minus its left-hand side just happens to be the sum of the variables. Okay. Why are slack variables important? Good question, you. It's because if I were to add in the slack variable to the left-hand side, what happens is this guy is 7 minus all that stuff that I have up there. And notice all that stuff that you have up there is right here. So what happens to these x's when I add the slack variable in? They just cancel. You just get equal to the right-hand side, 7. So when you add in a slack variable, it creates an equation instead of an inequality. The gap is intentional, by the way. It's getting us ready for something else. So that's the purpose of a slack variable. Slack, it means how much you have left over, right? So if you add back in the slack, then you have, it should be equal. Everything should be fair on both sides. Now, graphically, what is happening? Well, we learned from the beginning part of Chapter 7 that, hey, if you have this thing called a feasible region, all you really need to worry about is the corner points. The stuff in between, the shading in between doesn't matter. It's just the corner points that are important. The corner points came from the intersection of the equations. So by putting the slack back in, you're ignoring the shading in the inside, and you're only focusing on the equations themselves. So basically, you're eating the Oreo without the cream. Not as delish. I would still do it. All right, so that's the purpose of a slack variable, is to ignore the filling. You're only worried about the equations. Okay, good. Now, we just created some more variables, which means that we're going to bring back a word for the third time now that instead of just the x's, we also have the s's to worry about. So the x's plus the s's together can be written as a point, and those would be called augmented coordinates. Augment, remember, means to add on to. Hold on, my dog is chewing on something. What are you chewing on? Let me love you! I don't know what it was. I think it was tonight's winning lottery ticket. I was going to share it with everyone. Alright, augmented coordinates. So for this problem specifically, you would first list the x's, x sub 1, x sub 2, x sub 3, x sub 4, and then you would list the slack variables, s sub 1, s sub 2. Stop. Augmented coordinates, well, yeah, I'll say it that way. The purpose of augmented coordinates is to know where the point is in reference to the feasible region. Remember, we need the point to be a corner point. And since we have 4 x's here, we can't graph it. There's no way for us to look at a picture to know if it's at a corner. So augmented coordinates will tell you, hey, one of 3 things. This point is a corner point. Great. This point is inside the feasible region. Not so great. It's okay, but not what we really want. Or this point is completely outside of the feasible region. We want to avoid that at all cost. So the augmented coordinates tell us where the point is in response with respect to the feasible region. How do we find augmented coordinates? Glad you asked. Oh, I meant to use this slide for something else. That's okay. Let's actually, there is a video for that, but I want to make sure we do an extra one together. Let me duplicate this. So I'm going to make up a whole problem of finding augmented coordinates. And even though I said we're going to be out of 2 dimensions, we're going to go back to 2 dimensions just so we can see how everything is playing out. So I'm going to just make up x plus x sub 1 plus 4x sub 2 is less than or equal to 12. And then, oops, don't mean to do that, 2x sub 1 plus 2x sub 2 is less than or equal to, I can make that 12 again. Should I? Sure, why not? And then we'll say that x sub 1 and x sub 2 are greater than or equal to 0. Okay, so what I want you to do is pause the video and graph this region. Because when I come back, it's going to be graphed. And you should already be extremely comfortable with knowing how to do this. All right, pause the video. Okay. So hopefully this is similar, and hopefully you did a much better job than I did. What are you going to do? Okay, all right. So I'm going to pick like 4 or 5 points on purpose to illustrate what augmented coordinates are doing, and then I'll have you watch a video, and then we'll come back and do some more stuff. So I'm going to purposely pick the point 1, 1. I'm going to label it as A. I'm just going to put A over here. 1, 1. Don't finish off the coordinates. B, I'm going to make B 0, 3. Oop, I finished off my coordinate. You need to listen to yourself. I'm going to make C, let's make it 5, 5. 1, 2, 3, 4, 5. 1, 2, 3. 5, 5. We'll make D over here. This would be D, which is 12, 0. You know what? D think 4 is good. I think in the video I do 5, but this is sufficient. Okay, so what we're going to do is we're going to find the augmented coordinates. So again, it's x's followed by s's. How many s's do we need here? Hopefully you said 2. Remember, you need a slack variable for every functional constraint. We have 1, 2 functional constraints. So we need an s sub 1 and an s sub 2. Okay, so slack variables are found by taking the right-hand side, 12 minus the left-hand side, x sub 1 plus 4 x sub 2. Do the same thing. S sub 2 will be the right-hand side, also 12, minus the left-hand side, 2x sub 1 plus 2x sub 2. As a comment, what we're doing right now is demonstrative purposes only. You don't actually do this when you do this magical thing called the Simplex Method, but the results of this page is what's important. Okay, so in A, notice that x sub 1 is 1 as well as x sub 2. So to find s sub 1, we would put in 1 in for x sub 1 and 1 in for x sub 2. So 12 minus the quantity 1 plus 4 times 1, that's 5. So this gives us 7. So s sub 1 is 7. S sub 2, we're again putting in 1 in for x sub 1, 1 for x sub 2. Oh, I just told you the answer. 2 times 1 plus 2 times 1 is 4. 12 minus 4 is 8. So that means this is 8. Okay. That is how you find the augmented coordinates, is you just put in the x's into the formula and then you get the s's. So I'm just going to run through and finish the rest. Please make sure you get the same answers that I do. If not, let me know. Oh my gosh. 5 plus 20, 25. What is that? Negative 13. Alright, okay. 10, 20, negative 8. Okay. 12, 0. 0. And then 4, 0. Okay. Good. Alright. So let's talk about what all these points are doing. I need more colors. A. Where is A in reference to the feasible region? Notice point A is inside of the feasible region. Now look at the coordinates of A, 1, 1, 7, 8. What do all those numbers have in common that is not true for B, C, and D? Hopefully you said they are all positive. So when all of the coordinates of the augmented coordinates are positive, you are inside the feasible region. That's what A is saying. B. B, in reference to the feasible region, is a corner point. It's the intersection of the dark blue line, x sub 1 plus 4x sub 2 equals 12, and the y-axis, x equals 0, which comes from, stop it, x sub 2 equals 0, I should say. X sub 1 equals 0, I apologize. X sub 1 equals, stop it! X sub 1 equals 0. Okay, so with that, B is a corner point. What does B have that the other points don't have? It has two things going on. It has 2 zeros and the rest are positive. So compare that to D. It has 2 zeros, but the rest aren't positive. We'll get there in a second. So you know you are at a corner point when the number of zeros is equal to the number of x's and the rest are positive. I'll say that again. The number of zeros is equal to the number of x's and the rest are positive. That's a corner point. That's what we want. Woo! C. Well, C and D. Are C and D I'll just tell you. C and D are outside of the feasible region. completely. They don't touch it. They don't touch this shaded area at all. What do C and D have that A and B don't have? Hopefully you're saying negative coordinates. So if you have negative coordinates, that means you're outside of the feasible region, and that means something went wrong. So the moment one of your augmented coordinates is negative, stop. Maybe you missed type something in the calculator. Maybe you put the initial matrix in the calculator incorrectly. Lots of possibilities here. Whatever it is, something went wrong. That should never happen. Okay, now that's summarized on this page here. If you need to pause the video, great. But also, I would like you to watch video number 89, which basically goes over the last 5 minutes right now. So watch video 89 and then come on back and we'll talk about this magical thing called basic, non-basic pivoting. You'll love it! Boop! Okay, so going back to the previous discussion, we said that there is a point that all standard max problems have in common, and it happens to be the origin, 0, 0. So what we can do is we can force our problems in a standard max to start at the origin. And what happens graphically is you start at the origin, and then the simplex method tells you where to go, and what happens is you bounce from corner point to corner point until you get to the answer. That's basically the simplex method in a nutshell. Start at the origin, bounce around. The way we force us to start at the origin is by forcing all the x's to be 0. And that way you can solve for the slack variables. The values that are 0 are going to change as we go through the simplex method. So we have to come up with new terms. So we would say variables are non-basic if they are, oh, you know what? No, I don't want to do that one. We want to, do I want to start with non-basic? Yeah, I do want to start with non-basic. I didn't mean to do that. So a non-basic variable is a variable that is set equal to 0. And a basic variable is a variable that is solved for. So in the beginning of this process, we again need to force ourselves to be at the origin. The origin is where all the axes overlap, which means all the x's, in this case, x sub 1, x sub 2, x sub 3, are equal to 0. Because remember, this is x sub 2 equals 0, this is x sub 1 equals 0 in two-dimensional space. So if the x's are equal to 0, you're at the origin, which is great. Okay, so keep those two terms in mind. And again, as we move around the simplex method, and this movement is called pivoting, which we're about to do next, the variables that are basic and the variables that are non-basic will swap. All right. To pivot means two things happen. Turn the pivot element into a 1 and use the pivot element to turn other entries in the column equal to 0. Durr. To pivot means to turn the pivot element into a 1 and to use the pivot element to turn other entries in that column into a 0. Doth that sound familiar? Yeah, because that's just basically Gauss-Jordan. Make your 1, make your 0s. However, in Gauss-Jordan, as we saw, you could have used row 3 to change something in row 1 and row 2, or maybe row 2 to change something in row 1 or row 3, yada yada. There was no rules as far as which you had to use. In the simplex method, you are forced to use this magical thing called the pivot element. You cannot use anything else to make changes. Only the pivot element can make changes. The analogy I always do is stupid, but I apologize. It works like an Ouija board. You put your hand on it, and it tells you where to move. You don't tell it where to move, supposedly. So the simplex method will tell you how you have to proceed. You have no choice in the matter whatsoever. Okay, so that is how you pivot. And actually, let me see. Let's do an example of pivoting. Do I want to do that here? Yeah. So what I'm going to do is I'm going to go back to this guy, 1, 4, 12, 2, 2, 12. And we're going to create what is called, we're going to set up a little bit of this matrix I keep mentioning that's called a tableau. So what did I say? 1, 4, 12? And then 2, 2, 12. Okay. Okay. This matrix that we're about to create is not a complete matrix. We're going to add more onto it later. All right. So let's rewrite these equations. Let's rewrite these inequalities with the slacks in. So remember, we would be adding S sub 1 to the first one. There's a little button on this pen that I keep hitting, and I don't mean to, and I apologize. And now we'll turn that into an equation, and then we'll do the same thing. Oh, this should be a 1 here, not a 2. We'll add S sub 2 to turn that inequality into an equation. Okay. So the first one was the inequalities themselves. The second thing I just wrote now are the corresponding equations. And what we're going to do is create the matrix from this. We're going to have several headings. We're going to have BV, which will stand for basic variable. We'll have the X's, followed by the S's. Oh my gosh. That should be S sub 1, S sub 2. I apologize for that. And then when we get to this, we're going to be adding more columns to this, but this is the generic idea. And RHS, right-hand side. Okay. So notice this is the X1 column, X2 column, S1 column, S2 columns, right-hand side. So we're just going to, like we did before in chapter 6. So the first row would be 1, 4, 1, 0, 12. The second row would be 2, 2, 0, 1, 12. Okay. Oh, and BV. So when you are starting, the first basic variable is S1, and the next basic variable is S2. Why, you ask? Good question. Look underneath your slack variable columns in the very beginning. What do we see there? It's your identity matrix. The columns of the identity matrix identify the slack variables. So because we have a column here, 1, 0, where it's underneath S sub 1, and the 1 appears in the first row, that means the first slack variable is a 1. Likewise, here we see another identity matrix column underneath the heading of S2. The 1 now is in the second row, which means the second slack variable is S sub 2. Okay, so that's how you know which variables are basic. If the variable is basic, you read all the way across to the right-hand side to determine what the value is. So S sub 1 reading all the way across right here is 12. And S sub 2 reading all the way across is also 12. If it is not on the basic list, that means it must be non-basic. And what is its value? 0. So right now, X sub 1 and X sub 2 are 0. And S sub 1 is 12, as happens to be S sub 2. So the corresponding augmented coordinates for this problem would be 0, 0, 12, 12. Just coincidence that they both happen to be 12. So look at that. Are there the same number of zeros as there are x's? Yes. Are the rest of the coordinates positive? Yes. So we're at a corner point. This is great. Okay. Now let me do some erasing here, because I don't want these other colors to get in our way here. Okay. So now what we're going to do is do this magical thing called pivoting. To pivot again means to turn the pivot element into a 1 and everything else in that column into a 0. We don't know how to pivot. That's coming up shortly. But I'm going to demonstrate bad pivoting. So there's that. And then I'll have you guys try a problem which will have a graph involved. Okay, so I'm just looking real quick. We're going to pivot about this 4 here. So I'm telling you, not why, but I'm saying that 4 is our pivot element. So I need to turn that 4 into a 1, and then I need to make anything else into that column into a 0. You have to use the second elementary row operation to make 1s. You can't do anything else. Like for instance, if this 2 here were like -3, you can't say, oh, let's add that -3 to the 4 to make a 1. Nope, it's illegal. You have to use the element itself to be a 1. So how do you make 1s in that case? You would multiply by the reciprocal. And by the way, we're just going to do everything by hand here. Pretty soon we'll bust out the calculator. All right, assuming that pivot element is a 1. So now imagine there's a 1 where that circle is at. We need to get rid of that 2 that I already have an arrow pointing to it. What do you multiply the 1 by? So when you add it to 2, you get 0. Hopefully you said -2. So -2 row 1 plus row 2 makes row 2. Okay, so we're going to do those 2 operations. I'm going to fill in my columns. I'm sorry, my column headings. Okay, so 1/4 times the first row would be 1/4, 1, 1/4, 0, 3. -2 times the first row, adding it to the second row, well, -2 times 1/4 is -1/2, plus 2 is 3/2. This will give us 0. This will give us -1/2. This will give us 1 still, and this will give us 6. Okay. Look for your identity matrix columns. Notice we have one underneath the X sub 1, X sub 2 column now. That's great. The 1 is in the first row underneath the X sub 2 heading, so that means the new basic variable in the first row is now X sub 2. We'll do that again. Where's the other identity matrix column? It's still underneath S sub 2. Underneath the heading of S sub 2, the 1 is in the second row, so the second row's basic variable is S sub 2. Okay. Now let's declare what the augmented coordinates are. So X sub 2 read across is 3. S sub 2 read across is 6. If it's not basic, it must be non-basic, and again, non-basic is set equal to 0. All right, let's go through it. Do we have the same number of zeros as we have x's? Yes. Are the rest positive? Yes. So what just happened was we started the origin and we moved to the point 0, 3. Excellent. So we can actually go back to this drawing. So we started here, boop, and we moved up to 0, 3. Fantastic. You'll see that again in another example. Okay, so let's pick another pivot element. I will tell you what the element is, and then we'll do the whole pause the video, try it. I'm going to say, without destroying my thing, I don't know. I don't know what to pick anymore. It's really hard. Sort of want to make it that one. Yeah, let's make it the 1/4. Okay, so that 1/4 is the pivot element, which means that 1/4 needs to become a 1, and that 3/2 also in that column needs to become a 0. All right, so those operations would be for row 1 becomes row 1, and then -3/2 row 1 plus row 2 becomes row 2. All right, if you would, please try those two operations. And if you want to, also write down what the augmented coordinates are. Okay, so, oh, I forgot to write down my augmented coordinates. That's okay. So we would say that x1 read across is 12. x2 is not on the BV list, so that's 0. S1 is not on the BV list, so that's 0. And S2 is on the BV list, so read across -12. All right, do we have the same number of zeros as we have x's? Yep. Are the rest positive? Nope. All right. So that means the pivot element that was selected was not the correct pivot element at all. So what just happened graphically was we were at 0, 3, and then we went too far. We went to this point D that we already found the augmented coordinates for. We should have stopped here to stay inside the feasible region. So this is the dangers of picking the wrong pivot element. You could shoot accidentally outside of the feasible region. But the purpose of this slide is to tell you how to pivot, make the pivot element into a 1, turn everything else in that column into a 0. All right, if you would, watch video 90 is another example of what we just did with a graphical element as well. When you come back, we're going to talk about how to pick the pivot element, because that's the important part. So come on back. Okay, so there are 3 steps that need to happen to find the pivot element. To find the pivot element, you first find the pivot column by looking at the most negative number in the objective function row. Oh, we didn't talk about what an objective function row is. We'll get there. If there is a tie, pick the leftmost one. 2, find the pivot row by dividing the positive entries of the pivot column into the right-hand side and choose the smallest ratio. 2 huge words in number 2 that students overlook. 1, dividing the positive entries. Is 0 positive? No. Is -5 positive? No. What do you do with those numbers when you're doing step 2? You ignore them. You completely ignore them. It's like they're not even there. 3, the intersection of the pivot column and the row give you the pivot element. Okay, so let us do 2 things. We'll do an example of setting up this magical thing called the initial simplex tableau, and we'll also find the first pivot element. We won't actually pivot, we'll just get it ready. Okay, so let me make up a problem. Someone give me some numbers here. I can feel it. I can feel the cosmos. If you know what video game that's from, let me know. All right, 2x of 1 plus x of 2 plus 4x of 3. Subject to... I'm just making all this up. Like when I do my taxes. That's a joke. I don't do my taxes. Okay, so here is the math. We're going to turn that into more math by making an initial simplex tableau. So that's what this is formally called, the initial simplex tableau. Okay, in the initial simplex tableau, there are a couple new columns that we didn't have before, maybe just the one. We'll have the BV, that's supposed to be a B. BV column. We'll have x of 1, x of 2, x of 3. How many slacks do we need? 2, because we have 2 functional constraints. But we also will have a z column and then the right hand side. Okay. We're going to need 3 rows here. I'll explain why in a second. And we actually have a double augmentation. Hence those lines there. Okay. Now, if this were a traditional class like we were back to face-to-face, I would have you write out your equations. I would have you turn your inequalities into equation form like I have on this slide here. We're going to skip that. We're going to just go right to the good stuff. But again, if you need to, rewatch that portion or go back even further to where I defined the slack variable. So remember, s sub 1 would be related to the first inequality. So that would turn that into the equation. And then the coefficients of that row would be 1, 1, 4. You would have 1 s sub 1. In that row, you would have no s sub 2. There's no z. And your right-hand side is 10. Calm down. It's okay, love. And the second inequality turns into an equation when you add in s sub 2. You'd have 1, 5, 2. You'd have no s sub 1, 1 s sub 2, no z, 15. So again, just like I talked about, you would put in s sub 1 into the first one. So you have 1x sub 1, 1x sub 2, 4x sub 3s, 1s sub 1, no s sub 2, no z, and the right-hand side is 10. That's basically what I just did. Okay. So basically the first 2 rows that we just did is what we did in our previous one. The last row is reserved for the objective function. And recall that this guy down here, or up here, excuse me, is your objective function. To find the objective function row, what you do is you bring everything over to the left-hand side. This is the only time you bring everything over to the left-hand side when you are creating the initial simplex tableau. So if I brought over the 2x sub 1, it's now negative 2x sub 1. And if I brought over the x sub 2, negative x sub 2 minus 4x sub 3 plus z equals, if I brought everything over to the left, that means there's nothing on the right. Okay, using your column headings that you just made, the coefficient of x sub 1 is negative 2, coefficient of x sub 2 is negative 1, x sub 3 is negative 4, there's no s sub 1, there's no s sub 2, there's 1z, hilarious, and the right hand side is 0. Okay. To find the basic variables is just like before. Notice you look for the identity matrix columns. Here's s sub 1, here's s sub 2, and under z. Notice under all 3 of these columns in the beginning, you see the identity matrix columns. Since the 1 underneath s sub 1 is in the first row, then the first basic variable is s sub 1. 1 second row underneath s sub 2, s sub 2. And 1 last row underneath z, last one is z. Okay. So that whole thing is called the initial simplex tableau. And with that, we can now start this process of finding the pivot element. So step 1 is to find the pivot column. I'm going to use a highlighter. The pivot column is related to the most negative number in the objective function row. Objective function row remembers the last row, -2, -1, -4, 0, 0, 1, 0. Which number is the most negative? -4 is the most negative. So that is our pivot column. Okay. To find the pivot row, you take the positive entries in the pivot column. Which entries of the pivot column are positive? The 4 and the 2. That's it. We ignore the -4. It's not there. And this is the important part. We divide them into the right-hand side. So that means we would say 10 divided by 4, which is 2.5. And we would say 15 divided by 2, which is 7.5. So take the positive entries of the pivot column and divide them into the right-hand side. I forgot to say that earlier. That's the second important word, into. And we take the smallest ratio. Well, which number is smaller? 2.5 or 7.5? Good job, 2.5. So that means this is our pivot row. Where the pivot row and the pivot column overlap, you have found the pivot element. So that 4 is our pivot element. So then you would pivot. You would turn the pivot element into a 1, turn everything else into that column into a 0, and then you would continue. So again, the tableau tells you what to do. You have no choice in the matter. Okay, so this is the simplex method. Define the slack variables and write the initial simplex tableau. Okay? Select the pivot element and pivot. Great. Continue pivoting until there are no more negatives in the objective function row. And there should never be negatives in the right-hand side. If you get negatives in the right-hand side, that means you're outside of the feasible region. You picked the wrong pivot element. Very, very bad. And then as we did earlier, read across to find the basic variables. And the non-basic variables are equal to 0. The value for z is in the lower right. Okay. All right, that was a lot. This was a long, long video, but I told you that this was a long, long, long section. So what I want you to do is I want you to watch some more videos. Actually, take a break, really. I can't remember where I had you stopped. Did I do 91? No. So I need you to watch 91, 92, 93. 91, 2, and 3 will finish this section 7.4. 94, 95 will be 7.5. So you're basically watching up to 95 at this point. All right. Give them a go. Let me know if you have questions. I know this is heavy. This is probably the heaviest section of the entire course, and it's at the end. And I feel bad that I'm not there to help you out in person. But please reach out if you have questions. I am here to help you because it's always good to take breaks from Animal Crossing. All right.